This research explores artificial intelligence as a collaborator in landscape architecture through the integration of machine learning and adaptive public space design. The central research question asks, how can machine learning and interactive prototyping help identify the optimal gathering area within a public space while maintaining a human-in-the-loop process? Current AI applications in landscape architecture are often limited to visualization and image generation. These approaches provide limited spatial reasoning, minimal adaptability, and weak integration with real-world environmental conditions. To address this gap, the project proposes a four-step hybrid digital-physical framework consisting of data collection, model training, spatial prediction, and physical integration. A total of 120 spatial variations were generated by the designer using environmental and programmatic elements, including trees, pathways, and patterns of human activity. The resulting layouts were then encoded into structured spatial datasets using computer vision and will be used as inputs to train a machine learning algorithm. Using computer vision and spatial encoding, each grid configuration was translated into numerical matrices that could be processed by the machine learning model. A lightweight convolutional neural network was then trained to predict suitable gathering locations based on spatial relationships and environmental logic. The system produces a gathering space probability map, identifying areas with the highest spatial suitability while maintaining designer-defined constraints. The model analyzes spatial adjacency, clustering, and circulation relationships, learning patterns in a way similar to how designers interpret plans and spatial organization. This workflow establishes a continuous feedback loop between physical interaction, computational analysis, and adaptive spatial response. Users interact with the physical prototype by placing colored markers representing trees, pathways, activity zones, and open space onto the 4x4 grid system. The convolutional neural network evaluates these spatial inputs by analyzing proximity, clustering behavior, and adjacency relationships across the grid. The predictions are then translated into physical form through servo-motor actuation, allowing the prototype to dynamically raise or lower cells and visualize gathering space suitability in real time. Although the framework demonstrates strong potential, limitations remain, including simplified datasets, reduced spatial resolution, and mechanical constraints. Future work will expand testing, dataset diversity, and real-world validation. Ultimately, this research demonstrates that artificial intelligence can complement, rather than replace, human landscape design judgment by supporting adaptive, interactive, and evidence-based spatial decision-making.